Good morning, everyone. My name is Vijay Samuel. I'm a principal architect at eBay and work on the observability platform at eBay.
I'm Wei Tang. I have been working in eBay for 10 years now and have many experience in monitoring platform.
Today, we're going to talk about how to innovate on top of open source. So let's say it out loud. Observability is hard. And the scale challenges that are associated with observability are real. With regards to logs and events, you have volume. With the metrics, you have cardinality. With tracing, it could be that you have a lot of instrumentation, which causes a lot of spans, resulting in very large call chains. So basically, we are saying that I need everything at my disposal to debug. That is the first thing that every customer of an observability platform that says it. And I may need it only once in 10 years, but I still need it. I cannot risk having it. So observability is more or less an insurance policy that people use within the company. Open source is a great start, but there's always a but with open source. And these are some of the things that we are used to hearing. It's like organizations comes in different shapes and sizes. Open source usually optimizes for the greatest common divisor. You don't see a very successful open source project that is not very opinionated, meaning if they build anything and everything, eventually it becomes too complex and it's bound to fail. And that's one of the things that I personally like about projects like Prometheus is like there are a good amount of opinions that make it simple enough for us to use in the long run. And always it's the concern that the business wants what the business wants. I see that there is a common schema, but my organization wants to do it differently. And frankly speaking, we are in a position where we have to meet what the business demands. And sometimes a rarity where like there are a few companies that do things really well where they want to try different things, but they cannot do it at the pace of open source. Because sometimes it takes a long time for things to flush out in a way that it's useful for everyone. So, but how do I still do it? And I want to be honest, like this is not a pitch to say that, okay, you should fork open source and you should make changes yourself, but we are trying to see if there is a way in which we can do this while being within the community and at the same time maybe be on the bleeding edge or do things a little bit differently so that it works for the business. So what are suitable means to scale? The first thing is basically build on top of public APIs or public specifications, whether it be OpenTelemetry for ingest, Prometheus remote read or remote write if it's a metrics-specific implementation that you're looking for. And on the query side, when it becomes a reality, a query language that is standardized, that everyone can get behind. And this allows you, if you fix the ingest and the query, you can be as creative as you want in between. You can have custom stores for traces, logs, events like ClickHouse, or if it's Prometheus that you're looking at, you can think about how to shard, replicate, cluster the storage engine in ways that you would like. And there are several reference implementations for both of these kinds of patterns out in the wild. As long as the customer sees the open standards on ingest and query side, everything in between is fair game. So that is one of the principles that our observability platform inside of eBay has operated for the last decade or so. And as I mentioned, like we always want to try new things before putting them out. And the reality is that everything that we try doesn't necessarily end up being a success. How do we do it in such a way that, okay, we are trying something out. If it works, then we can raise a few PRs or GitHub issues to the community, get some feedback, and then merge it back into the greatest common divisor. So basically, anything that is successful, let's invest time with the community. Otherwise, we tried something, it didn't work, move on. So over the next few slides, we are going to talk about a few case studies on how we maneuvered some of the challenges that we have had with some of the open source projects. And the first one, I love Prometheus. Would love it more if it could scale horizontally. This is something that everyone, I think that there'd be tens of issues on the Prometheus repository where it's like, okay, can you support sharding? Can you support replication? And the answer is always no. So for this, we got a little creative. A few years ago, Google unveiled a paper called Monarch, which they dub as their planet-scale time series database. And they introduced a very a unique way in which how you can layer out your time series database. So Sherlock is the umbrella project for eBay's observability platform. And the Monarch paper asks us to layer the time series database in a way called leaf, zone, and root. So if you take a leaf cluster, you have the simple TSDB. And so think about the Cortex nomenclature for how they define their time series database. So you have your storage, you have ingesters that can write time series in, and you have the standard querier. So this is basically how Cortex operates today. Monarch basically asks you to come up with something called an indexer, which is nothing but a collection of fingerprints that basically say that this TSDB has these label key value combinations or these n-grams, which basically can select if you're doing a regex. And if the querier knows this, it basically knows exactly which TSDB has which sample of a time series database. So if you have one shard, then the indexer is going to say every time series is within that shard. But if you have n shards, you know exactly which shard has a given time series. So beyond this, everything is standard. Like you have a ruler, which can basically execute recording rules, send alerts to an alerter. You can have LTS, which is basically Thanos. But the interesting thing becomes that if I have another layer, which has more granular things like, let's say the leaf has pods. The zone has rolled up metrics that are across the entire namespace. As long as the indexer in the bottom propagates his fingerprints up, what the querier can do is the querier can look into that particular leaf if it needs more pod level metrics instead of just namespace level metrics. And you can keep stacking this up, saying that, okay, I'll keep rolling up, I'll have smaller amount of time series in higher regions and the finer ones in the lower one, and you should be able to scale it out. So this we did with the help of just the Prometheus TSDB, an implementation of the ingester and querier, which basically does a modified version of remote read and remote write, and our own indexer implementation. But the thing is that the user only sees PromQL, and they only use remote write to ingest in. So the natural question would be, why could we have not used Cortex and then maybe done this on top of Cortex? The unfortunate thing is that Cortex was not close to ready when we started this journey. And some of the design choices that we made is very specific to eBay. And we did things in a slightly more simpler way in which that we do no replication. It's completely shared nothing. We dedupe at query time. And most of the design decisions were learnings from what we learned from Google Monarch. So the things that really worked was the layered architecture that Google Monarch prescribes with leaf, zone, and root. We implemented a Kubernetes-based ring discovery, which basically says that, okay, discover using a stateful set name, you can find all the shards that the TSDB has. Or using a certain DNS, you can discover where the ingesters are, the queriers are, and things like that. We implemented streaming aggregations that allow us to drop raw cardinality from entering the Prometheus storage engine. And we use Prometheus as a library, like no modifications to Prometheus whatsoever, but packaged in a way that it can be deployed the way that we desire.
So our chasing journey started with ClickHouse. At that time, Jaeger did not support ClickHouse yet. Why ClickHouse? It has many good features. The first one is it is a columnar database, which means that it actually can achieve best compression rate for each column. And it saves lots of disk. And the second one is that it's very easy to set up and maintain. So all you need to do is just run a single cluster and define a query table, and you can query all the data that you have. And also there are many references out there for us to learn. So apart from ClickHouse, we also use Hotel Collector in our pipeline. And we also expose Jaeger API for our end users as well. We learned a lot. I would like to share few big learnings. The first one is large classes. They are hard to maintain in the end. This is simply due to the limit for each single Kubernetes cluster. And the second one is single table or a white table. They normally hold all the data in one table, but this design does not work well for all query patterns. The third one actually took us for long to learn. The distribute table, it will become much slower when number of shards increase at some point. So it actually takes longer on network instead of scanning data. So we broke rules. First, we build many smaller clusters and we use ring service to manage them. The ring service will show them as a global virtual cluster. And then we write spans based on trace ID. That means a single trace will store in a single shard. And we normalize our schemas. This is our schemas. The index table will store some metadata. And we also have traces and traces symbols table to store spans. And we store exemplars in sample traces ID table. We also have other tables like so the service operation table to serve some query pattern. Okay, the third case I would like to show is service graph connector. We use it, but not that easy. The connector can generate metrics from spans, and the metrics will be stored in metric store for much longer, like 1 year. The way it works is that it stores spans in memory to match incoming spans. Unmatched spans will be held for much longer, like 5 minutes or 10 minutes. And another bad news from our side is that we would like to add root service and root operation as labels in the metrics. It is undoable without holding all spans for one trace in memory. And we have to wait the whole trace to complete in memory as well. But our data volume is super high, so we cannot do that. We start from our database. We write a custom receiver on Hotel Collector, which will fetch traces from our database, and then pass spans to the service graph connector. So it's simply just match spans. Unmatched spans can be skipped. This is the flow. So we write spans to each shard, and then we run Hotel Collector, which has our receiver to fetch spans from each shard, and then generate metrics and write to metric store. We got many benefits. So the first one is that we actually don't need to enhance the service graph connector. And the second one is that it reduces loss of memory. I mean, we actually don't need to hold spans more than 1 second. And we also don't need to move data around across regions as well. And also we can use with other process in the pipeline. Back to Vijay.
So I think one of the things that is worth mentioning is that some of these problems only show up in scale. And if you take our organization specifically, we have roughly 4,000 microservices that are there. And when you have those many microservices, for things like Service Graph Connector to work in the prescribed way, you would have to do one of two things. You either host all those 4,000 in a single Kubernetes cluster, which probably is impractical, or you basically say that I have a second layer of OpenTelemetry collectors that are there, where you load balance by trace ID and make sure that you're bringing all the spans of a given trace ID into a single collector, and then have the decision being made. But then you introduce other side effects that are there. You have to hold the span trace in memory for you to be able to generate the whole thing. And with 4,000 microservices and arbitrary kind of SLOs that each of those microservices might have, holding all of them to make sure that you're actually completing the trace becomes a very challenging task. So basically, the approach was to go backwards, like wait for the trace to come to rest, give it maybe a 5-minute offset or something, and then pull and then generate the graph. Yes, the graph will be delayed by 5 minutes or so, but at least the correctness is there. You eliminate the need for network for moving all these spans around all the time, and also you're saving so much on memory. So the last case study is basically, wouldn't it be great if I could do more with alerts? And for this, we did an experiment with the alert manager, and we asked ourselves, can we enrich alerts before they are sent off to their corresponding notifiers? And we asked ourselves, like, what would happen if we enrich alerts with the sample trace IDs, specifically trace IDs that match the alert that we are sending right now? It would result in faster triage. What would happen if you are able to group trace alerts based on what root cause it might be associated with it? Again, it would allow faster triage. Or if there is an alert that's there, I'd like to know if it's noise. And if it's noise, I would like to just suppress it. That would again result in faster triage. So a little bit of post-processing on the alerts could really speed up triage. That is the hypothesis that was there. So what we tried to do is basically add custom stages into the alert manager pipeline. So alert manager, the standard pipeline has a gossip phase, there is an inhibit phase, there's a mute phase, dedupe, and then finally retry. So this is the boilerplate pipeline that was there, and we identified, okay, which place within this pipeline, if we insert some custom code in, would we be able to do something more? And let's take the sample trace ID use case. So stage is a public interface on the alert manager repository. So we wrote our own stage that basically says that look at an alert, fetch the underlying PromQL that was there, fetch the exemplars that were associated with that underlying, do some simple processing. So let's take a latency case, right? Like if someone has an alert against the 90th percentile of latency greater than say 5 seconds, we would basically say that, okay, eliminate all the exemplars that are less than 5 seconds and only show ones that are greater than 5 seconds, and put them as an annotation into the alert. So that way you can have your Slack template or your PagerDuty template, look at the annotation, and then paint it nicely on the alert. So when someone sees the alert, they can just click the sample trace. And if you have listened to the talk that was given in KubeCon London, we have an explainer that can explain this trace. Immediately you know what is the causal span or the causal service that is causing this issue. So this basically would allow us to debug faster in theory. But it's challenging in the sense that we dreamt of something that the alert manager was not really built to handle. Alert manager cannot handle simultaneous updates of alert objects. It would cause alert manager to panic. So we did two things. We mitigated it internally with some hacking so that like it still works for us. But like we raised it with the Prometheus community during the last KubeCon. We were asked to raise a few issues. Because it's a reasonable feature to ask. And hopefully, either through a contribution from us or someone who wants to, this will become a part of the greatest common divisor. So out of this, all of these, like, what did we gain? Like, we were able to scale, number one. And a lot of these things that we have done helps us to triage faster. And we are doing it with open source and without forking. Our goal within the organization is to make sure that we are able to achieve high levels of availability for our customers and be able to do it in a way that is sustainable. And we are able to do that and give back along the way. So these were a couple of the issues that we raised as part of our experiment with the alert manager. The first one is to allow mutating of the alerts, and the second one is to allow limits to be imposed and min-max values that we can filter on for exemplars, so that we are only getting meaningful exemplars when we are requesting. And for this and in the past, like, we have been active community contributors to projects like OpenTelemetry, Prometheus, and whatnot. So my closing message is, like, yes, open source can be challenging to adopt at scale, but it is not the answer. Forking is never the answer. And as a community, exchanging all these nodes, contributing, we can definitely take some of these projects far higher than what they already are, and benefit each other along the way.